doped semiconductor, and then they should meet to make a junction. But it's not that you take two semiconductors and join them to make a junction, one p-type and one n-type. You start with the same material, same wafer. If I talk in terms of silicon, the first thing is that you should have a very, very pure silicon material, and there are processes, well-controlled processes by which you can grow very pure monocrystal silicon, and then they make some kind of cylindrical tubes, or not tubes, just cylinders, solid cylinders, and then you can cut wafers of appropriate size. The impurity level has to be very, very slow if you want to make devices out of it, electronic devices out of it, and that impurity level must be, let's say, less than 1 part in 10 to the power 10. So that's the starting material, and with this starting material, the first thing is this entire wafer is made either p-type or n-type, this whole thing. So let's say we make it p-type. To make it p-type, you have to diffuse trivalent impurity like boron or something, so it goes there. Here also you have very controlled processes. There are several processes by which you diffuse these impurities, and at the end you retain that silicon crystal. Silicon I am taking as our model semiconductor. In any kind of semiconductor you have to do all this processing, and so through very controlled processes, without finally disturbing that crystal structure, you have to put these impurities at those lattice sites. So this whole thing becomes p-type, and once this whole thing becomes p-type, after that you, in a very controlled fashion, you diffuse n-type, and for that some pentavalent impurities like arsenic or antimony. So that is now diffused in a much more controlled manner, so that it goes only up to some depth. So this side still remains p-type, but here dopants of pentavalent impurities are driven into this, they are diffused into this in a larger concentration. So this side becomes n-type, and this side remains p-type. So you have p-type here, you have n-type here, and this is the junction. This is that junction. So this is p-n junction. And if you want to use it for external world, you should have metallic contacts from where you can connect wires and put this into circuits. So very controlled fashion, once again, part of that metal is deposited aluminium, or some metal is deposited either on the back side or on the front side itself. You can have a P here and metallic contacts. So for our discussion, I'll be drawing this part of, let's say, this part of this system. So I'll write it, or this part of the system. So I'll show it in the diagram many, many times, maybe 20 times. P-n junction as a rectangle like this, and then a line in between, and then one side is n side, one side is p side, like that. So what I'll be actually showing is this portion. This is n-type, this is p-type, here's the junction, here's the metallic contact, here's the metallic contact. So this is, I represent this as a metallic contact. You'll assume that you have a metallic contact here, you have a metallic contact here. So this is the situation. Now if you do create this kind of a p-n junction, it is an absolutely unstable situation, because this is n-type. What does it mean? It has huge number of electrons, large number of electrons, conduction electrons. Because of those pentavalent impurities, you have large number of electrons here, conduction electrons here, free electrons here, and you have some holes here. You have some holes here in between. Small amount. Remember, Ne into NH, that is fixed, Ni square. And for a ppm type doping, we had calculated that the number of holes reduces to a few thousands per centimeter cube, but they are still there. And similarly, on this p side, this is p-type semiconductor here, so you have a large number of holes. You have large number of holes here, and then some electrons in between. There are some electrons in between. So on the n side, you have majority carriers, that is E electrons, and minority carriers, that is H. On p side, you will have majority carriers, that will be H, and minority carrier, that will be E. Now since this is that same crystal on which you had put these impurities, all kinds of movements are possible. Electrons can go from this atom to this atom to this atom to this atom to this atom. The holes can also go from here to here to here to here. So all that usual electron movement and hole movements is allowed in this entire wafer, in this entire material. And therefore, having large concentration of electrons here and having a very small concentration of electrons here is a very, very non-equilibrium situation. If you have such a huge concentration gradient, and if the movement is allowed, they are allowed to go from here to here. So remember, the whole thing is one single crystal on which you have done all this diffusion, and therefore that movement is allowed. So if you have concentration gradient, you have large concentration of electrons here and very small concentration of electrons here, naturally there will be a systematic flow of electrons from the higher concentration side to the lower concentration side. Yeah, it's a law of nature. You put your incense here in one corner of the room, and then this entire room gets that particular aroma flavor, and that is because the concentration of those particles here is very large near that incense stick, and the concentration is low in other parts of the room, and then there is a flow from higher concentration side to lower concentration side. So if this is the situation, you will have a systematic flow. We call it diffusion, systematic diffusion. Diffusion itself is some kind of systematic flow. So of electrons in this picture, it will be from left to right, and of holes in this picture, it will be right to left. And keep track of what is happening in the actual crystal. This is the diagram on which we make, but if you think of actual silicon crystal, keep that also in mind so that that physical connection is not lost. So you have all those silicon, right, all those silicon atoms. Then at some places, if it is n-type, you have put those impurities, and because of that you have those electrons, extra electrons, which are in the conduction band, and they are going here to there, to there, to there. They are just going randomly changing atom to atom, atom to atom, and so on. So in the process, they are going from this side to that side to this side. But since the concentration of electrons is large here, the number of electrons which are going in a given time from this side to that side, this side to that side, will be much larger than what can come from the other side, and hence there is a net flow. And similarly, holes. If you have holes here, if you have large number of holes here, some holes can diffuse to this side. Hole diffusion, you remember, the bonded electron breaks from here, and then there was already a hole here, a broken bond was here. So a new bond is broken here, and the electron, bonded electron goes there, and the hole is filled here. So this hole has gone from here, and new hole is created here. We say that this hole has diffused. So since large number of holes are there, once again, the diffusion of holes from right to left in this figure will be much larger than the diffusion of holes from left to right. And hence what will happen? Hence you will have a charge density appearing. Remember, when you dope n-type or p-type impurities, the charge density does not change, it remains 0 in the entire thing, because whatever you dope is neutral. The wafer is neutral, the dope atoms that you are doping, they are also neutral. So this entire charge density is 0. But now there is a systematic movement. Electrons going from left to right, what will they do? They will create a negative charge density here. And then these holes going from right to left, that will create a positive charge density here. Electrons leaving itself is creating positive charge density. So both ways, holes coming from here, electrons going from here, both ways you will have positive charge density on this side and negative charge density on this side. So you have a charge appearing, rho, which is positive. Okay, rho which is positive here, and a charge appearing here, rho which is negative. So in a n-type or p-type semiconductor, if you just have one semiconductor p-type, you do not have charge density. But if you make this junction p-n junction, then the charge density will appear. You will have positive charge density on one side, negative charge density on other side. But this thing doesn't extend up to the end. Close to junction, this will happen, and away from the junction, the situation is still neutral. So this charge density appears only in a small portion which is close to junction. Why? That is because once the charge densities are there, you will also have an electric field. Okay? If the positive charge density is here, negative charge density is here, you will have an electric field like this. And this electric field will oppose.
Okay? If the electrons are trying to come from left to right, and the electric field is also in the same direction, the force on the electron is in opposite direction, negative charge, and therefore that force will resist diffusion, will oppose diffusion. Similarly, holes coming from right to left, holes behave like positive charges. So the force, well, you understand, holes behave like positive charges of certain mass, and therefore we can still talk of force on the hole and all those things, but that force on the hole is in the direction of the electric field, that is towards right. Holes are trying to go towards left, so this will be opposed by the electric field. And then there are some other processes I will be talking about. So ultimately, this charge density which appears here, all that happens close to this junction, say in a layer like this. Now, if the electrons are coming to this side and the holes are sitting here, these electrons will have a good probability of filling up these holes. So the electron which has come, the charge carrier, the negative charge carrier electron which has come from left to right, finds so many holes there, and therefore one or the other hole will definitely invite it, and it will accept that invitation gladly, and then it will go and fill that hole. What will happen? That electron, suppose this electron has gone from here, and it meets this hole, it fills this hole. So now there is no hole and there is no conduction electron, that pair is gone. Similar thing will happen everywhere. Holes which are coming to this side, they will also combine with the electron. What does that mean? Holes are coming from this side, that means a bond is broken from here, and this hole comes and fills that, and then okay, hole is created here, so this electron goes from here to here, this broken bond is filled by this electron, and therefore this hole has gone from here, it has come to this side, and then this electron has filled that hole, so that is also over. So in that same fashion, you will have no charge carriers left. The electrons which are diffusing to the right, because of the large hole density there, they are trapped. And then if there are holes left, more electrons will come, and this width will be adjustable. So as many holes are here, as those many electrons will go from this side and fill, and both ways, from this side to that side, that side to that side. So what you find is, yes, there are charge densities, but you do not have charge carrier density. Okay, so that number of electrons per centimeter cube, this, or number of holes per centimeter cube, this is 0, this becomes 0, this becomes 0. 0 means negligible. One or two here and there may still be there, but to be observable in a circuit. So this is almost 0. So in p-n junction, charge density appears in a region close to the junction. Right? So close to the junction, there is a region in which charge density appears. On n side, you have positive charge density. So this is 1. And then on n side, rho is positive, and on p side, rho is negative. And another interesting thing is in this region, there are no charge carriers. So the charge carrier density that is almost 0 for all practical purposes. Ne and NH, they become 0 only in this region, okay. So this particular region is known as depletion region. This is called depletion region. This is the region which is depleted of charge carriers. It doesn't have charge carriers. That is why it is known as depletion region. Now, what is the width of depletion region? How much will be this width? That depends on the concentration of the dopants. Okay, remember the dopants are there. This is n-type up to here. From here to here, this is n-type, and p-type from here to here. So although there are no charge carriers, this is still n-type material. So we have diffused those pentavalent impurities here. So although the charge carriers are not there, the conduction electrons are not there, the holes are not there, but still those pentavalent impurities that we have put in, arsenic or phosphorus, they are still there. They are distributed in this entire region. This is still n-type region. And similarly here, although there are no charge carriers, no holes, no electrons, but still it is p-type. So the width of this depletion region on the left of the junction and on right of the junction, that will depend on the concentration with which that dopants was put there, the impurity concentrations. All right. So n-type is we call it donor ions. So Nd, donor ion concentrations. The one we have doped. So this is it. And this side is acceptor. So this impurity is acceptor. So this is the number of acceptors that we have doped per unit volume. So that is here. And that decides this width. If it is large, if you have large concentration of impurities, then in a very small region, you have enough those electrons. Suppose this is large, Nd is large, then you have in a very small region, you have enough electrons which can go and neutralize that layer there. Similarly, Nd, Na and Nd, this they will decide. Larger this impurity concentration, smaller will be the width. So if Na and Nd are not equal, you can have unequal width on the two sides of the junction. So those
result in the number of electrons in the doped material exceeding the number present in a pure semiconductor. The number of implanted impurities can be controlled using the fabrication technology. A semiconductor containing these impurities is called an N semiconductor, since it has negative charge carriers. The impurities are named donor impurities, since they donate electrons. An impurity with only 3 electrons in its outer shell can also be used. The 3 outer electrons complete 3 of the 4 bonds. The 4th bond remains unoccupied. However, at room temperature, the electrons from other bonds can move in to occupy this free space, creating a hole in the material and a negatively charged impurity. As in the previous case, the number of implanted impurities can be controlled using the fabrication technology, so the number of holes in this doped material can be much greater than the number of holes in a pure semiconductor. A semiconductor of this type is called a P semiconductor because it has positive charge carriers, and these impurities are named acceptor impurities since they accept an electron. A p-n junction is a structure formed by neighbouring regions with different dopings, p-type and n-type semiconductors. The p-n junction is a crucial part of many devices, such as, for example, the diode. If a positive voltage drop is applied between the p-terminal and the n-terminal of a diode, a large current can be observed experimentally. If we change the connectors and a positive voltage drop is applied between the n-terminal and the p-terminal, an extremely small current, negligible for most practical applications, is observed experimentally. The p-n junction shows this asymmetric behaviour. The current can flow in one direction, but not in the other. This is a peculiar behaviour which enables a wide spectrum of applications in circuits. To understand this particular feature of the p-n junction, we must consider 2 mechanisms that create an electric current: the diffusion mechanism and the drift mechanism. One way to understand the diffusion mechanism is to imagine 2 sets of different coloured particles concentrated in 2 distinct zones. If the particles are free to move in different directions, their random motion tends to equalise their concentration in the whole volume. Diffusion is the physical mechanism which gives rise to free particles trying to occupy the maximum possible volumes of a p semiconductor perfectly matched to an n semiconductor. The p semiconductor has a much higher hole concentration than the n semiconductor. Therefore, holes from the p region will diffuse into the n region. Similarly, electrons from the n region will diffuse into the p region. The diffusion of electrons and holes creates a region depleted of free charge particles, leaving behind the ionized impurities from which these charge particles come. Thus, a region of positive ionized impurities and a region of negative ionized impurities appear in the p-n junction. This special distribution of charges creates an electric field. The electric potential associated with these fields acts as a barrier that prevents the displacement of the electrons and holes. Equilibrium is reached in regions, the barrier height is reduced. A reduced barrier cannot prevent electrons and holes from diffusing across the structure. An electric current appears in the junction due to the diffusion mechanism. Under these conditions, the p-n junction is said to operate under a forward bias. If the voltage is reversed and becomes greater in the n than the p region, the barrier height increases, preventing the electron and hole diffusion. The electric current is then negligible. In conclusion, the p-n junction can only conduct in a single direction, giving rise to a current which increases very rapidly when the potential barrier
are the things. Now, in this depletion region, you will have electric field, this electric field here, because you have charges, you have positive charges on this side, you have negative charges on this side, rho is positive here, rho is negative here, so you will have electric field. And because of this electric field, the potential, electric potential, will decrease as you go from left to right in this picture, right? You are going along the electric field. So if you go along the electric field, potential decreases. E is minus dV dx. Okay, if I call this as x direction, then as you go, if the electric field is in x direction, then E minus dV dx. So potential decreases. That means this n side should be at a higher potential than the p side. We are not connecting any batteries. We have just to put neutral impurities in a neutral semiconductor wafer. But we see that some electric field appears in this depletion region. In this region, there is no electric field because it's still neutral, no charge density. And here, this is still neutral, no charge density. And effect of this will cancel out here. Okay, effect of this will cancel out here. So you don't have any electric field here. So potential is same from here to here. Right? From here to here, the potential is same. But then the potential starts decreasing. And here, up to here, it decreases. And then from here to here, the potential remains the same. So if you think of these metallic contacts here and here, now the potential here is larger than the potential here because of this electric field. And you may think that, okay, that's very nice. I have gotten a battery. I have a larger potential here. I have a lower potential here. So let me connect a bulb. And if this is a higher potential, this is a lower potential, this bulb should glow. The current should go, at least momentarily. But it doesn't happen like that. It doesn't happen like that. Because here also you have different kinds of materials. You have the semiconductor, doped semiconductor here. And then you have the metal here. So once you go from a semiconductor to a metal, there is junction out here. So you do have a potential difference here also. As you have a potential difference across this junction, you also have a potential difference across this junction, and similarly across this junction. So here also semiconductor to metal, there will be a contact potential difference. Here there will be a contact potential difference, and here also there is a potential difference. And when you sum all these things, this potential, finally it's same as this potential, this V1 and this V2. Contact, after the contact, you have V1 equal to V2 after those metallic contacts, and so this bulb is not going to glow anymore. So in our next lecture, we will derive a relation between this potential difference that is created, which is also known as potential barrier. Why potential barrier? If you remove that or don't think of the metallic contact, we are still in the semiconductor, and then if I plot the potential as a function of x, how will it look like? This potential is higher and this potential is lower. So up to this depletion region, up to here, the potential is constant. And after that, the potential will gradually decrease once you enter this depletion region because of this electric field. So it goes like this. And then again, it will become constant. So it will be like this. So this is how the potential as a function of x will look like. This is that depletion region. Okay. Well, it's not, don't match. This is the potential. This is the depletion region. And if you think of electron, the energy of electron is Q times V, negative of that. So if you plot another graph, which is energy U, of the electron, if you plot energy of the electron and then x here, and since it is negative, this whole thing will flip. Okay, so if electrons try to go from this negative side to that positive side, n type to p type, this side left to right, if they try to go here, and if they have some energy, say this is the energy of the electron, then it finds that okay, there's a barrier out here. There's a barrier out here. If the electron has this much of energy, then okay, then this electron can go into this region. But if the electron is having this much of energy, it cannot penetrate in this, at least classically. So this height, this difference is known as, or same as this difference. The units are different. This is voltage, this is energy. So this difference is known as potential barrier. It opposes the diffusion of electron from n-type side to p-type side. So in our next lecture, we will derive the relation between this potential barrier and other parameters of this p-n junction. Right? So you have a region, say up to here, and then here up to here, you have some region where you have no charge carriers. But then the charge density is there. Since these electrons are going to this side, everything was neutral, so you get negative charges here. And then these holes which are going to this side, they create this positive charge here. Right? So initially everything was neutral, and then you bring some electrons from this side, you shift some holes from this side, both of them will create negative charge here and positive charge here. So you have rho, charge density rho, which is not 0, but the charge carrier density, that is 0. So this whole region where you do not have charge carriers, that is known as a depletion region. So this region is the depletion region. These holes have gone here to neutralize these electrons, or the electrons have come here to neutralize these holes here, and therefore the charge carriers are not there, that's fine. But then at any temperature, we told earlier that any temperature, new whole electron pairs are created, because in that material you have thermal distribution. These electrons can get energy from the crystal of the order of this Boltzmann constant K times T. So because of that thermal distribution, energies are taken up, energies are given away. So new electron hole pairs are always created, and old hole electron pairs are destroyed in normal semiconductor. So that process is still here in this depletion region also. New electron hole pairs are created, but since you have an electric field here, in this picture we have put positive charges on this side, so the electric field is towards left. So since you have an electric field here, as soon as a whole electron pair is created, holes will be swept away towards left, this side, and the electrons will be swept away on the opposite side. So this region still remains carrier free. Right? So that is this. Then we said that okay, once you have electric field, you will have some potential variation also. In this case, now the potential is decreasing from right to left, so potential will decrease. So this will be at a higher potential, this will be at a lower potential. There will be a potential difference between this n side and this p side. Of course, you have metallic contacts. Again, you have potential difference at this contact also. So finally, if you see from outside this connection here and this connection here, no potential difference will appear. You cannot light your lamp because of this potential difference that is created. But inside this material, yes, potential difference is created. And if you look at the energy, so the energies are opposite, electron energies, because it's minus E times V. So here the electric field is this side, potential here is smaller, potential here is larger. But if you talk of energies, these energies will be up and these energies will be down. Okay, so let me talk today a relation between these weights, this weight, and the potential difference, the electric field, and all those things. Let us make some calculation on that. Suppose this width is x1 here, and this width is x2 here. So the junction line is here. Then this depletion region extends up to depth x1 on this p side, up to depth x2 on the n side. And these x1, x2, they depend on the dopant densities. How many impurities per unit volume you have put here, and how many impurities you have put here. So if this is a p type, that means you are putting acceptor impurities here, so Na, and here you are putting donor impurities, so Nd. How many acceptor impurities per centimeter cube, how many donor impurities per centimeter cube, that will decide this. If you have large density here, and if you have smaller density here, and if these holes are to neutralize these electrons, or these electrons are to neutralize these holes, a small width is sufficient to neutralize a larger width here. And therefore x1 and x2 will be different. And you can always have this relation, rho times x1, rho times x1, rho 1 times x1 is equal to rho 2 times x2. If this is here, rho is equal to say minus rho 1, and this charge density is rho equal to plus rho 2. Then this rho 1 times x1 in magnitude is equal to this rho 2 times this x2, because total charge has to be 0. Total charge has to be 0. Everything is neutral. So it's only migration of electrons and holes from this side to that side and so on. So the total charge must be 0. So if this is say rho 1, and assume that it is uniform from in this width x1, and this is plus rho 2, which is uniform in this width x2. And then when I'm drawing this line, you understand it's a plane. It's a planar area. You have this semiconductor material, and junction is a layer. Junction is a plane layer. On one side you have P, one side you have N. So I'm drawing on a line. It is in fact a surface area. So that surface area times x1 will be the volume. Volume times charge. This ρ1 charge density will be charge here, negative charge. And similarly, this volume area times x2 is the volume multiplied by ρ2. That will be the positive charge. And they should be equal in magnitude and opposite in sign, so that the total is 0. This assumption of uniform charge density is not very bad, in fact. If I plot ρ here and x here, in this case you have negative charge, and in a smaller width I'm showing, so it's like this. And this side is positive charge, and I'm showing larger width, so it's like this. This is, if we call x equal to 0 here, this is x is equal to minus x1, and this point is x is equal to plus x2. This height here is ρ2 here, and this is minus ρ1 here. And this area ρ1 times x1 should be equal to this area ρ2 times x2. So this step function type is of course an approximation, but it's not very bad approximation. If this density, this dopant density is uniform in A and Nd, it should result this kind of a charge distribution. So let me now calculate, if this is the charge distribution, what will be the electric field distribution? How electric field will vary as a function of x. So let me draw another diagram, and I'm only now showing you the depletion region. I'm only showing you the depletion region. So this is x1, and this is x2, and this is the junction. So up to here you have that negative charge, minus ρ1. In this whole thing you have minus ρ1, and in this whole thing you have plus ρ2. And suppose I need electric field at this point, at some distance y, which later I will call x, or let me call x, at x, electric field at x. This is x equal to 0, the junction is x equal to 0. So at distance x, in that n-type side, I'm putting a point here. What is the electric field at this point? Okay. So what I can do is, I can first calculate the electric field due to this minus ρ1 charge here, and then I can calculate the field due to plus ρ. So let's first do this. Let me take a small width here. This is at some distance x, and this is dx. So that charge which is here, this charge. What is the electric field due to this at this particular point? So this you can treat as a surface charge layer, and that surface charge density sigma will be this volume charge density ρ1 and times this dx. All right, since it is a thin this layer here, I'm taking dx, so I can treat this whole charge as on a surface charge layer, and then the total charge will be this minus ρ1 times dx times that area, that will be the charge, and then I divide by the area to get charge per unit area, and that will be this much. And so the electric field due to this will be dE1, let me call it dE1, that will be sigma over 2 epsilon, and it is minus ρ1 dx over 2 epsilon, and this epsilon is epsilon naught times k, and this k is dielectric constant. Right? In free space, in vacuum, or in air, effectively, if you have a surface charge layer of surface charge density sigma, the electric field in front of it is sigma over 2 epsilon naught. Since this whole thing is in silicon, not in free space, so we put this dielectric constant also, and it becomes sigma over 2 epsilon. Then you integrate from here to here in this entire region, entire width x1, so that dx will be integrated to x1, and so E1 will be equal to minus ρ1 divided by 2 epsilon, and then x1. This is the field at this point because of this whole negative charge here. Okay. Then come to the second part, this part. So here, let me do it in two parts once again. Let's draw a line here, and this is all plus ρ2. So first calculate the field due to this part, which is to the left of the point chosen. Okay. So once again you can do the similar analysis, and here again you can take a small dx. Again here you can take a small dx. By the way, this was negative charge, and so the electric field that we have calculated, yeah, we have put the minus sign here, so it is in this towards left. Now this is the width dx I am taking. This dx I am taking. This is now over. This part is over. So this dx I am taking. And once again, you can treat this as a surface charge layer of surface charge density plus ρ2 dx. And dE2 will be, again, because of this, what is the electric field here? So sigma over 2 epsilon. So plus ρ2 dx over 2 epsilon. So what is the electric field due to this part, which is positive charge plus ρ2 to the left of the point chosen? So what is this whole length? This whole length is, this thing is just x. So E2 is equal to plus ρ2, I'm writing from here, divided by 2 epsilon, and then this dx is integrated here to here, which is just x. What remains? This part, electric field due to this part. So let's calculate that also. So this dx is also over. So now let me take a layer here, this dx, and because of this you calculate what is the electric field here, and then integrate from this point to that point. So once again you can write dE3. So dE3 will be, the sigma remains the same because this is plus ρ2, so ρ2 times dx. So sigma remains the same, ρ2 dx. dE3 is sigma over epsilon naught, which is ρ2 dx over 2 epsilon naught, but now it will be in negative direction. right? This will be in negative direction because you have positive charges here. You have positive charges here, and you want electric field here. So because of the positive charges, the electric field will be towards left. So we put a minus sign here. So that will be dE3. And when you integrate this and write what is E3, that is the field due to this whole part to the right of the point chosen. Remember, always remember, I am trying to find electric field at this point, which is at a distance x from this junction. Okay, so at this point. So the third part is electric field due to this much, and that will be, when you integrate this, you will have minus rho 2 over 2 epsilon, and then this dx. Now dx, when you integrate, you get this length. And how much is this length? How much is this length? This length is x2 and minus x. x2 and minus x. So it is, E3 will be x2 and minus x. So now I have all three contributions. First contribution is due to this entire negative charge which is sitting here. This is that p-type semiconductor left to that junction depletion layer. So this part here, this part here. This is the depletion region. This is still p-type because all those impurities, acceptor impurities are here. So it is that part. So because of this, then on the other side, E2 is from that other side of depletion region from here, but only from the part which is left to this point where I am calculating electric field, and E3 is the electric field due to the rest of the system. So this is the thing. Now you calculate what is the total. So the total is, so the total electric field will be E1 plus E2 plus E3, and that is minus rho 1 x1, so minus rho 1 x1 over 2 epsilon naught plus rho 2 x over 2 epsilon naught, and then minus rho 2 2 epsilon and x2 minus x. And this rho 1 x1 I can write as rho 2 x2 from here. Okay. So this is rho 2 x2, so I can just replace it here itself. This is rho 2 and this is x2. So you see rho 2 over 2 epsilon is common, I can take it out. What is left? Minus x2 plus x, then minus x2 and plus x. So 2 times x and minus 2 times x2. So you can write this, you can put minus sign outside, minus rho 2 over 2 epsilon, because that 2 can cancel. Okay, and then you have x2 and minus x. Since x2 is greater than x, that's why I am writing x2 minus x and a minus sign here. So if I plot for electric field, here is the plot for charge density. If I make a similar plot for electric field as a function of x, taking towards right as the positive, how will it look like? It will be like this. Now I am plotting this E here, and this is x. This is the point x2, let us say, and this is that point minus x1. And I have calculated for this region only. This is negative, so this electric field will be on the negative side. At x equal to x2, the electric field will be 0. So here the electric field will be 0. And how much will be electric field at x equal to 0? At x equal to 0, E will be minus rho 2 x2 over epsilon. So it will be somewhere. It will be somewhere. This is the point. Let us say this is minus rho 2 x2 over epsilon. And then it is linear. Then it's linear. It's linear in x, so it has to be a straight line. And therefore you can join these two. This is the electric field. This is the electric field on this positive x side. You can do a similar calculation for electric field in this region, this part. You can do a similar calculation here, and you can just guess what it will be. When I did this, I get electric field at this x equal to x2 as 0. Do exactly similar analysis, and you will get electric field at this x equal to minus x1 as 0. So the electric field will be 0 here, and so this is for x less than 0. This was for x greater than 0. In the depletion region, remember. After the depletion region, after x2, there is no electric field, and this electric field just goes like this. And on the other side, for x less than 0, what you will expect is that at x equal to minus x1, the electric field will be 0. And the same expression here at x equal to x2, electric field is 0. So at equal to minus x1, it will be 0. And then at x equal to 0, from the same expression, if you go, your electric field should be minus, it was rho 2 x2 here, so it will be rho 1 x1 here divided by epsilon. But it's same as this because rho 1 x1 is equal to rho 2 x2. So it's same. It should be. And therefore, the electric field will be like this. So this is how the electric field will appear. It will be linear in the two regions. Depending on the dopant density, you will have a certain slope of this E versus X line here and here. So our next task will be to calculate the potential as a function of X. Once I have electric field, I can calculate the potential using our equation E is equal to minus dV dx. So we can calculate this of a potential difference. This is dV is equal to minus E dx for one-dimensional case. And so here it will be rho 2 over epsilon and then x2 minus x and dx. So if I integrate, you get V is equal to rho 2 over epsilon, then x2 minus x square by 2 with a minus sign because you have negative sign here, and plus some constant. And that constant can be evaluated by just choosing a point for V equal to 0. So we take this junction point itself, x equal to 0 itself, as the point where V is 0. That's our choice, you know that. So take V equal to 0 at x is equal to 0, and then you get 0 is equal to, x is 0, so it is minus rho 2, x is 0, so x2 square, and divided by 2 epsilon, plus c. So c is rho 2 x2 square by 2 epsilon. So you can write this from here, you can put that c there, and you get v is equal to minus rho 2 over 2 epsilon, and then x2 minus x square, and minus this x2 square. So let's check at x equal to 0, v should be 0. So at x equal to 0, it is x2 square minus x2 square, that is 0, that's fine. So we have substituted it correctly. So this is the expression for v. And what is v at x2? v at x2. At x is equal to x2, v is equal to, so x is equal to x2, so this goes out. So it will be rho 2 x2 square over 2 epsilon. Right? You put x equal to x2, so this is 0, this is plus rho 2 x2 square by 2 epsilon. It's a quadratic function. It should be. If electric field is linear, then the potential has to be quadratic. So if you plot, how will it look like? So the expression was v equal to minus rho 2 over 2 epsilon, and then x minus x2 minus x square, and minus x2 square. So at x equal to 0, this is 0, and x equal to x2, it is at x equal to x2, it is v equal to rho 2 x2 square, and then divided by 2 epsilon, right? This is 0 here, and then rho 2 x2 square, and by 2 epsilon. So if you plot, if you draw x this direction, v this direction, it's 0 here, and then this is say rho 2 x2 square over 2 epsilon, and at x equal to x2, it must be this much, so it's here. And then it's quadratic. And also remember, the slope of this v versus x is electric field in magnitude. And here the electric field is like this. So the magnitude of electric field is largest at the origin. So v versus x should have largest slope at the origin, and then as the electric field decreases, the slope should decrease, and at x equal to x2, the slope should become 0 because the electric field is 0. So it should be of this kind. It should be of this kind. Right? So that should be the kind of plot, quadratic, joining this point, and slope gradually increasing. Slope gradually decreasing as you increase x, and beyond x2, right? Beyond x2, that means in your p-n junction, this is x2 and this is minus x1. So beyond x2, here in this region, this is the depletion region. So in this region, there is no electric field, and so the potential is constant. So throughout this n-type region, this is n-type, throughout this n-type region, the potential remains constant like this. Same is the story on the p side, x less than 0. X less than 0, if you write, is the same algebra, identical, and this v will be at x is equal to 0, we have taken v equal to 0 anyway, and at x equal to minus x1. It should be quadratic. Remember, the electric field is just of this kind, so linear, so it has to be quadratic. And at this point, you can take the similar expression from here. V is minus rho 1 x1 square by 2 epsilon. So if this point here is minus rho 1 x1 square over 2 epsilon, and this point is x is equal to minus x1, then you have to join this point and this point. So this comes like this, and then it turns, and here the slope should become 0, and then it should become constant. So that's the kind of potential variation across this junction as you go from p side to n side. So this is at a lower potential, this is at a higher potential. There's a built-in potential inside this material. No batteries, nothing, but there's a built-in potential difference here. And this difference is known as the potential barrier. This difference is the potential barrier. You give some name to it, let's say call it VB. So how much is that VB? That VB will be this rho 2 x2 square by 2 epsilon plus this rho 1 x1 square by 2 epsilon. So VB will be rho 2 x2 square and plus rho 1 x1 square and over 2 epsilon. That's the barrier. It is in terms of rho 1, rho 2, x1, x2. Let us try to write that width of depletion region. Width of depletion region, relation between that and this potential barrier that we have calculated. So what we are interested in, that width of the depletion region, which is x1 plus x2. x1 plus x2. This x1 and this plus x2, this is the total width of the depletion region. You have one more relation, and that is rho 1 x1 is equal to rho 2 x2. Right? Charge neutrality, rho 1 x1 should be equal to rho 2 x2 because the charge here is minus rho 1 times x1 times that area of cross section, and the charge which is here will be similarly minus plus rho 2 x2. And since this total should be 0, after all we have not put any charge in this material, so this relation. From these we can write capital X in terms of VB rho 1 rho 2, eliminating x1 and x2. So first step is write this rho 1 x1 as rho 2 x2. Use this equation here. So this is equal to, this VB is equal to rho 2 x2 square plus rho 2 x2 and x1. right? This rho 1 x1 is rho 2 x2 and one more x1 here. So it is this. And you take rho 2 x2 common and you get x2 and plus x1, which is capital X. So this is one. Now you have to eliminate this x2, and that you can do from here. This x1 and x2 are in inverse ratio of rho 1 and rho 2, and the sum is capital X. So x2 will be rho 1 divided by rho 1 plus rho 2 and times capital X. And x1, I don't need that, but x1 will be rho 2 divided by rho 1 plus rho 2 and then capital X. Okay, if you add these two, what happens? If you add these two, you will have rho 1 plus rho 2 in the numerator, which will cancel this rho 1 plus rho 2 in the denominator, and it will be x. So x1 plus x2 is capital X, this equation. And if you multiply this x2 by rho 2 and this x1 by rho 1, they become the same. So rho 1 x1 is rho 2 x2. So this is it. Use this expression of x2 here. What do you get? You have rho 2, you have capital X, and then 2 epsilon, and then this x2. So put rho 1, so rho 1 here, and then capital X, so square of this, and then divided by rho 1 plus rho 2. That is this VB, potential barrier. So if you want to write capital X from here, this capital X will be, take this thing here and this thing down and then square root of it. So it is 2 times epsilon rho 1 plus rho 2 divided by this, multiplied by this VB here and divided by this rho 1 rho 2 here. All right, X square, so this will go here, 2 epsilon rho 1 plus rho 2 into VB and then divided by rho 1 rho 2 and then the square root. So this is it. So you have a relation between this depletion layer width and this potential barrier, but this rho 1 and rho 2 are coming here. Okay, you can write this as 2 epsilon and then VB and then 1 by rho 1 plus 1 by rho 2. These rho 1 and rho 2 are related to the concentration of impurities that we have doped, right? Because how are you getting charges in the depletion layer? In the depletion layer you are getting charges because you have put impurities. This is p side, so you have put acceptor impurities. Acceptor ions are there, right? When you diffuse boron, for example, or any trivalent atom in silicon, then you have created a hole there and then the ion which is there, and this whole thing is neutral. So same thing is here, same thing is here. Here holes are still there, and therefore there is a charge neutrality. There is a charge neutrality, and here the holes have migrated to this side and recombined with electrons, or electrons have come here and recombined. This charge carrier has gone. So those ions which are there, those will still remain there. The hole has moved and recombined and has gone away. Therefore, you have this negative charge. All right. So each acceptor ion which is sitting there in the depletion layer is giving you 1 unit of negative charge. So the charge density will be just E times and this density of acceptor ion. So this rho 1 here, okay, this charge density rho 1 here in this region is just E times Na. What is Na? Number of acceptor ions per unit volume, right? Number of impurity ions which I have doped here per unit volume. So that is Na, density, number density. And then each ion has this charge of minus E, and therefore this rho 1 is just E times Na. And similar is the story on this side. Similar is the story on this side. On this side you have put donor ions. If it is silicon, you have put pentavalent impurities here, and this pentavalent impurity comes with extra electrons. So those electrons were there, here also, and this whole thing was neutral, but from here the electrons have gone, and therefore those positive charges will appear here, those donor ions, each donor ions, and will give you 1 unit of charge, E plus E charge, and therefore rho 2 will be E times Nd, density of donor ions. And this expression you can write in terms of Na and Nd, because these are the quantities which are under our control. We dope things, so we know what is Na and what is Nd. All right, so what is the final expression? So this X is equal to square root of 2 epsilon VB, and then here I write 1 over Na and plus 1 over Nd and E here. So that's the relation. So if you increase this concentration, what will happen? If you increase Na or Nd or both, what will happen? This increases, so this whole thing decreases and this decreases, right? So heavier is the doping, smaller will be the depletion layer, and vice versa. Okay, so that's it. Now this VB is something which still we do not know, right? So, and that VB in fact depends on, that also depends on the dopant concentrations and also on temperature. So I'll not give you those derivations, but I'll give you the expression for this VB in terms of those impurities and the temperature. And that is, this VB is KT divided by E, then log of, on the natural base, Na Nd over small ni square. You remember we have introduced all these symbols. This is Boltzmann constant, this K into T, Boltzmann constant into temperature in Kelvin, electronic charge. Na and D are the densities of acceptor and donor ions, and this Ni is the Ni is just Ne and NH, which are equal for intrinsic semiconductor before doping. So that is this Ni. So this gives you this expression for Vb. All right. So the next thing I will take up is the energy band diagram of this semiconductor, this p-n junction, and the effect of this potential difference that is created, internal potential difference that is created on the energy band diagram. So if there is no potential difference, you only have a p-type semiconductor and n-type semiconductor in the same original material, then the conduction band is here, the valence band is here, all these energies are valence band energies, all these energies are conduction band energies. So you have this bottom edge of conduction band here and the top edge of the valence band here. So same is the case with p-type, same is the case with n-type if there is no crosstalk between them. So the other side also is like this, same. Essentially what I am trying to do is I am mapping this area, this p side and this n side. If there is no diffusion, nothing, no internal potential difference developed, it's just this much is p-type, this much is n-type, and what is the conduction band, what is the valence band, where are those energies for this entire thing. If you draw it should be like this. But it doesn't remain like this because of this. On p side, the potential has gone down. The potential has gone down. That means systematically you are changing the energy levels, all the energy levels upshift, right? Because what we are showing is the electron energies. These are the energy levels for electrons, and therefore potential and energy, you will have a negative sign in between, right? Energy is Q times V, like that. So if you have an energy level somewhere and then this extra energy is imposed, right? So that much shift will be there. So since the potential here has gone down, and therefore the energy will go up, each energy level will go up by Q times and this much of amount. So relative to the n side, let's do it relative to the n side. N side and p side, the energy levels are shifted by different amounts. So relative to the n side, what happens? This p will go up by this much of energy. Q times energy, electron times E times Vb, this much is the total shift in each of the energy levels which are there. So if I keep this here, each of these energy levels will be shifted up. Each of these energy levels will be shifted up. So my diagram should be rewritten, and I have to, this edge will now go somewhere here, and then you have all those energy levels. Okay. I'm just drawing relative to that n side. It's not that it stays here and only this shifts and so on. I'm only looking at the difference. Similarly, this edge of the valence band, that also shifts up by the same amount, and therefore it's like this. Why I have erased this much? Because this much of difference appears only away from the depletion region. Let's say this is the depletion region, after which the potential is constant here, So this difference that I have calculated is from here to here. That means well on the left of the depletion layer and well on the right of depletion layer. So that is this. And inside the depletion layer here, when you see a gradual decrease here. That shift gradually decreases. So if I take this as the reference, the shift is this much here, 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 and shift is this much here. All right. So gradually it will come and join here, like this. So that's the kind of energy diagram you will have. These are your valence energies, valence band energies, and these are the conduction band energies. So the band is shifted like this. This is p side and this is n side. This is the depletion region and so on. Now at this stage, I would also like to introduce a very important term qualitatively, and that is called Fermi energy. But that will be in the next lecture.
And if you write the energy bands, conduction band and valence band, say if this is EC and this is EV, so conduction band is here, the valence band is here, and if this is well away from this junction in the p side, so this is p side, and then you have a bending out here, like this. This is n side, which is far away from the junction, and then you have conduction band, quantum states here, then you have quantum states here, valence band, quantum states here, and so on. So you have this kind of bending of band as a function of distance from this junction. Now we call it a barrier in the sense that if you consider an electron here, conduction electron here, and let's suppose it is in this particular quantum state, and if this electron moves towards the junction and tries to migrate into the p side, what happens to it? It can come up to here, that's fine with this energy, but then there is no quantum state available here, and so it cannot penetrate, it cannot go into the junction, into the depletion layer, and then to this p side. But if you have an electron, all these are quantum states, you have an electron in this quantum state, let us say in this quantum state. So again you take an electron in n side, conduction electron, but it is occupying a much higher quantum state. So if that turns in this direction, if that comes in this direction, then with that same energy, it can really completely go into p side, it can cross the depletion layer. So for these electrons, this barrier is not surmountable, at least classically, but for these electrons, this barrier is crossed. The kinetic energy will decrease, all those things will happen, but it can still cross over. So it becomes very important to find the occupancy of these quantum states. If you have conduction electrons here inside, you have a lot many conduction electrons here. How many of those electrons are in these quantum states? How many are in these quantum states, in these quantum states, in these quantum states, in these quantum states, and so on. So the distribution of electrons in different quantum states of different energies is very, very important if you want to calculate the currents and anything. And to get that distribution, how many electrons are in these energies, how many electrons are in these energies, and so on, you need a very important concept, a parameter which is known as Fermi energy, written as EF. So I'll write a function which is known as Fermi function, and then I'll tell why I'm writing this, what is the significance. This is F, let's call it F, small fe. It's a function of energy, and it is written as 1 over 1 plus e to the power E and then minus EF and then divided by KT, Boltzmann constant times temperature. This particular function represents the probability that an electron will occupy a quantum state at this energy. Okay, so I repeat, you have these quantum states, but and each quantum state can be occupied by an electron or it can be empty. No two electrons can go in one quantum state. So if I ask that, okay, this is the energy, at this energy I have a quantum state, what is the probability that an electron is occupying this? So that probability is given by this function. It depends on temperature, and this is the energy at which this quantum state I am asking, and this is the parameter. This EF Fermi energy is the parameter which you have to keep same. This quantum state, this energy, this energy, this energy. So as a function of energy with a fixed EF and at a fixed temperature, you can calculate the probability. So this Fermi function gives you probability that a quantum state at energy E is occupied. Now if you plot this function, first let us plot it at t equal to 0, capital T equal to 0, and see what happens. If you plot this function, Fe here and E here, and suppose this is EF, and suppose t is 0, okay. So if t is 0 and this is in denominator, so this will be infinity, okay, infinity. And if E is less than EF, it will be e to the power minus infinity, and e to the power minus infinity is 0, so this function will be 1. So for all energies less than EF, this function will be 1. So that means if you are at 0k, then all energies, all quantum states with energy less than EF will be occupied by the electrons. Probability is 1. And if E is greater than EF, then it is e to the power plus infinity, which is infinity, and this probability will be 0. So the function here is 0. So that's the kind of function at 0 Kelvin. But if you raise the temperature, if you come at say room temperature where K into T is 0.026 electron volts, and then you have some EF and at some energy, you are asking what will happen? This gets modified, but still the modification is close to this EF only. So if this is EF, then the function looks like this. The function looks like this. So it's again close to 0, much beyond this EF, this is close to 0, and well before this EF it is almost 1. And whatever is the change, it doesn't sharply fall, it falls gradually, but that change is only in a small region, and this region will be few times kT. The order of this width will be in kT, few times this kT. So that's the kind of thing. So if you are say 100 kT times to the left, probability is almost 1. If you are 100 kT times on the other side, the probability is 0. But then if you are say 2-3 kT times this side or that side, then you can have this probability. Okay, so now let us use this function to get probabilities in intrinsic semiconductor, p-type semiconductor, and n-type semiconductor. So in intrinsic semiconductor, we say that you have small number of electrons here only because of thermal thing. Some electrons jump from there to there, and you have some holes here. Where is the Fermi energy? The Fermi energy is, this is intrinsic. So Fermi energy is almost at the middle. This is EF. So these quantum states are also far away from here. Okay, far away means this is, for silicon for example, this gap is 1.12, so half the gap will be 0.56 electron volts, right? And KT is at room temperature 0.026 eV. So this is 0.56 eV and this is 0.026 eV, so it's far, far away. And therefore the probability that an electron will be here in this quantum state is very, very small. And that is why you have very small number of electrons which are able to reach here. And for holes, the probability, once again, if you look at here, again, this is much below EF. So the probability of occupation is very close to 1. You are in this region. It's very close to 1. So probability that it is not occupied, which is 1 minus Fe, so that there is a hole there. That probability is again very, very small, and so only few holes will be there, much less number of holes will be there. So that's the kind of picture when you have intrinsic semiconductor. And if you have a p-type semiconductor, what happens? If you have p-type semiconductor, you know, you have the conduction band here, and you have a valence band here, and you have lot many holes and few electrons. So where do you think is the Fermi energy? The Fermi energy is close to this EV. So that this is close, so you are close to the Fermi energy, you are close to the Fermi energy, slightly below this, so slightly left to it, you are somewhere here. The probability is less than 1. The probability that there is an electron is less than 1, and therefore there is a probability that hole will be there. If you are here, that probability is very small, but if you are here, there is some probability. If you are right at EF, the probability is half. Okay, right at EF, if you put E equal to EF, then you get this e to the power 0, which is 1, so 1 by 2. So if you are right here, the probability is half, and if you are close to it, okay, the probability is not half, but still sizable probability. So lots of holes are here. Very few electrons are there, even less than this intrinsic case. Okay, you know that when you put this p types impurity, then not only that you have lot number of holes, this electron Ne, that also goes down, because you know that Ne into NH is equal to Ni square. So if this increases, this decreases. In this picture, since we have gone even far away from this Fermi energy, initially the Fermi energy was in the middle, so we were this much away. Now you are this much away, so the probability has again decreased, and you have much less number of electrons here. So here the Fermi energy is like this. Whereas if you have N-type semiconductor, what happens? In N-type semiconductor, you have lot number of electrons, conduction electrons, and very small number of holes. So here the Fermi energy is close to this EC. So that it's close to Fermi energy, slightly above that. So the probability is quite sizable. Probability of occupation of these quantum states by electrons is quite sizable. So you have lot many electrons here. Whereas these holes, these quantum states, they are far, far away from this, and therefore it's very, very small, and you have only small number of holes here. Okay, so that is how. So this probability is almost 1 minus Fe is very small, and therefore very small number of holes are there. So this is the picture. Now for any given system which can interact with each other, parts of which can interact with each other, and it is in equilibrium. Equilibrium means nothing is changing as a function of time. Things are happening, the dynamic things are happening, electron holes are being generated, and recombination, all those those things are happening. This side electrons are going to those side, the holes are, anything is, but as a function of time, things are having same values. That is thermal equilibrium. So once the system is in equilibrium, it has to have only one Fermi energy, and therefore when you make this p-n junction, when you make this p type and n type on the same wafer, and then they can interact, in that case what happens, this Fermi energy and this Fermi energy has to be the same. So this whole thing has to be lifted, or this whole thing has to be brought down, so that this line matches with this line. So in this picture we have done that. In this picture your Fermi energy will be somewhere here. Your Fermi energy will be somewhere here. Okay, so for that p type it is close to the valence band edge, for n type it is close to the conduction band edge, and so on. So this is it. And once you know this EF, then using this you can calculate what is the probability of this quantum state being occupied, and this quantum state being occupied, and this quantum state being occupied. So if you have let's say 10 to the power 16 electrons per centimeter cube here in this band, you have doped these many electrons are there, conduction electrons are there. So how many of them will occupy this one, how many of them will occupy this one, and so on. You have one parameter. The probability of occupation of this one is given by this expression, this probability of this, probability of this, probability of this. So you put different energies E, and you can get the probability. So as this function shows here, if I draw this once again here, you can see that if this is EF, then the probability of these states will be large, occupation of these states will be large. As you go away and away from EF, then the probability will decrease. But that's not exactly the number of electrons which are there in this range. Suppose you take a small dE here. These quantum states are very closely packed with each other. So one by one quantum states I cannot discuss. So if you take a width dE, and then the number of quantum states will be there, and how many electrons will be there in these quantum states in this energy. If you need, this probability is needed, yes, but something else is needed. Something else is also needed. What is that? That is how many quantum states are available here. The quantum states are not uniformly spaced here to here. You have a distribution of quantum states. The probability at the bottom of this conduction band is largest, but then the number of quantum states here is smallest. You have very few quantum states available. So although the probability is very high, but then the number of quantum states is very small in this dE. In that case, the number of electrons will be very small in this dE. Whereas if you go up here, the number of quantum states in this dE is very large as compared to this. But then the probability is very small. So to get the actual number, you need both the things. This is the probability, and another thing which is needed is called density of states. This is another very important concept, density of states. What is this? You take some band, some width, some energy width, dE, add some energy E to E plus dE, E to E plus dE. Consider this. And then ask the question, how many quantum states are there? Number of quantum states in this dE. How many quantum states are there in this energy range? Not electrons, quantum states, occupied or not occupied. How many quantum states are there in this? And it turns out that if you make a calculation, this is proportional to, or divide by dE, that will be the density of states. So if this number is dN, then this dN over dE, this quantity is known as a density of state. You can write it capital dE. This is called density of states. Okay. So in the conduction band, it turns out that this dE is proportional to square root of E minus EC. there are some factors here, but energy wise this is the dependence, and this is EC. Remember, the bottom of the conduction band I am writing as EC. The bottom of the conduction band I am writing as EC. So the number of states, quantum states available in a given DE, that is proportional to this. So that means as you increase E, this number is going to increase. At E equal to EC, right at the bottom of the conduction band, this number is 0. So if I plot this DE here, let's say this is energy E, and this point is energy EC, and this I am plotting DE. How will that go? This DE is proportional to E minus EC square root. So at E equal to EC, it should be 0. And then it is proportional to this, so it will go like this. This is how this density of states will change. At the bottom of this conduction band, this density is 0. That means if you just take very small DE, you will have very small number of quantum states here. But as you go up in energy, the number of quantum states is increasing. This DE is increasing, density of states is increasing. So you, in the same DE, you will have more quantum states here. So that is how it goes. You can plot this DE here also. If I draw a line here and energy is going up. So this is EC. This point is energy EC. This point is energy EC and energy is going up here. And if density of states, this DE I am plotting on this side, right? Okay, energy is going up and this DE I am plotting towards right. What will happen? Here is 0 and then it will, see here how it is going. The slope is going down, down, down. So here it will be like this. As I am increasing the energy, here I am increasing the energy, is bending like this. So here I am increasing the energy, as bending like this. So this will be your DE, density of states. And what happens to this probability on the same graph? So in this graph, if I plot, it will be like this. Say at EF it is half, and then it decreases as you go up like that. Okay, so that is how Fermi function looks like. You go away from the Fermi energy, your probability decreases, and then it becomes almost 0. So it goes like this. So look at this. The probability is decreasing. You are going up. The probability is decreasing. There is a quantum state out here. There is a quantum state out here. This quantum state has larger probability of being occupied. This quantum state has lower energy, lower probability of being occupied. But how many quantum states are here? There are more number of quantum states are here and less number of quantum states here. So if you want the number of electrons in a given DE, number of electrons in E to E plus DE, E to E plus DE, for that you have to take care of both the things, this density of states as well as the probability of those quantum states to be occupied. So you have to multiply these, and therefore this will be F of E multiplied by D of E and then DE. Okay, this gives the number of quantum states in that energy range, and this gives the probability of each quantum state being occupied. So this will be the total number of quantum states occupied, or in other words, total number of electrons, conduction electrons in that DE. So if you do that, one is increasing, another is decreasing as you go up. If you multiply them, what you will find is the following. Let me make some space here to do that. So one function is going like this, another function is going like this, and when you multiply them, what you get is some kind of a function which maximizes and then it decreases of this type. Okay, so right at the bottom you do not have maximum number of electrons because the density of states is very, very small here. Slightly above it maximizes and then it decreases. Okay, but for all practical purposes, you can neglect that variation here, and you can say that lower the energy, larger are the number of electrons, and then as you go up, that number decreases. Similar will be the case with holes. Large number of holes here. The distribution will be like this. Here, let me modify this. So this is n side. The Fermi energy is very, very far away, so you have very small number of holes here, like this. The distribution is similar. You have larger number here, lesser number here, lesser number here, but total number of holes is very, very small here because this is your n side. And here you have large number of holes because this is the p side. Okay, so here you have large number of holes, and once again, close to this edge you have large number. Then as you go away, because remember this is your EF, this is your EF. So from Fermi energy, as you go away, this number is decreasing. But for these holes, this particular hole, if this wants to go in this side, no possibility, no state here. But if this hole tries to go this side, yes, there is a possibility. The quantum state is there, so this can migrate. Okay, so the diffusion can take place, electron going one side, hole going other side, all those things. And then there will be another very interesting thing which we call drift current, because if you don't connect a battery to the p-n junction, don't connect a cell, you cannot have a net current. So if diffusion is possible, something has to compensate for that. That is known as drift current, and that will be our next topic next day. Not at the bottom, but a little bit above. But we are not concerned with this, we are mostly concerned with this. So here the concentration decreases exponentially as you go up in energy. Similar is the story for p side. Here you have holes. So you look for the probability of not occupying this particular quantum state, 1 minus Fe. So that gives you probability of a hole being there in valence band. And then once again you have large number of holes here, and then as you go down in energy, this will exponentially decrease, and these quantum states will have lesser and lesser number of holes. So all these things we discussed. Then if there is a concentration gradient, we have diffusion. But which electrons take part in diffusion? Here I cannot say which electrons take part in diffusion, but here we can, because you have this barrier, because of this energy barrier. You have this energy barrier here. You have this much of energy barrier. And so these electrons cannot diffuse. If these electrons try to go from n side to p side, crossing this depletion region, there are no quantum states here. Only these electrons which are above this level, which are above this level, only these electrons which are in these quantum states, they will be able to reach here. At these energies, you have quantum state here on this side, and therefore they can only reach here. The more energetic one can reach here. Similarly is the case for these p-side holes. If these holes, these mesotic carriers, if they want to go to n side, then these holes cannot go here. You don't have any quantum state. Only the holes which are here in these ones, only these can migrate here. Okay, only these electrons can migrate here. So these are the electrons and these are the holes. But such migration will take place because of the concentration gradients. The electrons will try to diffuse here, and then the one which are having sufficient energy, they will go, and therefore you will have a current. This is the current because of this electron diffusion. You can call it I diffusion because of electrons, and the direction will be opposite to the direction of electron movement. And here, because of this hole going this side, you again have a diffusion current. You can call it I diffusion because of this holes, and the direction is once again the same, and so you have I diffusion, which is equal to I diffusion because of electron plus I diffusion because of hole. So you have a current from p side to n side. In this diagram, you have a current in this direction, I diffusion. But then we have not connected this p-n junction to any circuit, no cell, no battery, nothing. It is just lying there on a table. So how can there be a current through this junction, through this system, without charges being accumulating at some places? This is all steady state that we are talking of, thermal equilibrium we are talking of. All this inbuilt potential difference and this energy difference and barriers, all after everything is settled. You cannot keep on sending this current without connecting any battery or something. So what is the other mechanism? We have talked of majority carriers. We have not talked of minority carriers. You also have minority carriers. And how those minority carrier comes? If you have electrons here, if you have holes here, from where they are coming? The majority carriers come because we have doped the system with impurities, and minority carrier comes because of the thermal energies. Because of the thermal energies, whole electron pairs are continuously created and continuously destroyed also. Recombination also takes place through some mechanism. So you have recombinations and you have thermal generation. Those things keep going in any part of this semiconductor material, and these minority carriers are essentially coming from that. And that process takes place throughout. So you have here also in the depletion region also EH pairs are created and also EH pairs are destroyed. But then you have electric field here. Okay, in this picture, the electric field is in direction n to p, because all these negative charges will accumulate here. You will have negative charges. Those ions, those impurity ions being exposed because the hole has migrated or it has recombined. So those ions are exposed. You have positive charges here. So you have electric field. So as soon as this EH pair is created, this electric field will exert force on this newly created electron here, and that electron will be pushed in this side and the holes will be pushed in this side. So that mechanism also you can understand from here. If there are minority carriers in the depletion region or close to the depletion region, somewhere here, let's say these are generated, suppose it is generated here, then it diffuses into the depletion layer and then this electric field takes over. So if you think of those minority carriers, this is p side here, so a lot of holes are here and some electrons are there. And where are they sitting? These electrons are sitting in the conduction band. Right? These are the minority carriers. And if these minority carriers, because of this electric field, these electrons, they will tend to go towards that n side, so they will tend to go in this direction. These electrons, they would like to go in this direction, and there is no barrier. There is no barrier. They can very easily go. This electron can go, this electron can go, this electron can go, everything can go. And similar is the story for this n side. Here, the electrons are in majority and holes are in minority, and these holes are here in the valence band. If they want to go towards this p side, no one stops them. No one says that no, because you have all quantum states available. So this barrier is not a barrier, rather it's something which helps. If there is the electric field which pulls, here the electric field which pulls it on the other side. So you will have, because of this minority carriers, you will have a current. And what is the direction of that current? The electric field is taking these electrons from p side to n side, and therefore the direction of current will be in this picture from right to left. So because of this, you have a current which we call drift current. Anything that is in the influence of this electric field, that is known as drift. So it is drift and the direction is in this direction, right to left. And here also the holes are going, these minority carriers, these holes are going from right to left, and the current is also from right to left. So you will have I drift. So this I drift is because of the electrons, and this I drift is because of holes, and that is also going right to left because holes are positively charged. So holes are going from this side to that side, so that's also the current direction. So you add these two and you have drift current. I drift, which is I drift because of electron plus I drift because of holes. And that is in the direction of n side to p side. Diffusion was in the direction p side to n side, and drift is in the opposite direction. And in equilibrium, when you have not added any external circuit, there is no final net current, and so these two are equal in magnitude. Okay, so these two are in equal in magnitude, giving you net current 0. So that is when your PN junction is just lying on the table, the activities are on, thermal generation of minority carriers are taking place, electron hole pairs are being generated, and recombination is also taking place. There are some nice mechanisms which are different for different kinds of semiconductors, so I will not go into that, but it is happening. And then because of majority carriers, you are having some kind of migration of charges, then you have minority carriers, they are also contributing another kind of currents, but the net total current is 0.